Okay, good afternoon, everyone. Welcome to the session. This is the last session today. I hope all of you will enjoy the session. Okay, I am Lisa. I'm from Intel. My main work is open source storage related, and currently I'm working in the Ceph community. Over the last 2 or 3 years, I have been working related to BlueStore and RocksDB to do some performance tuning and improvement. Okay, so currently I am working in the NIB RBD part, that is client side. Okay, Tushar is the part in our team, and he is the architect of Ceph in Intel. Okay, we worked in the same project. Okay, so we have a team which worked in the Ceph community. Our work is to upstream and contribution to the community. I'm proud that we are the top 5 contributionists in the Ceph community. Yeah, and about our teamwork. Currently there are mainly 2 parts. One is in the client side. We have 2 parts. One is the shared read-only cache, which provides shared read-only cache on the persistent device. Okay, this part has been implemented and merged. Okay, the other part is the write-back cache on persistent device. This part is ongoing. Okay, another part is Crimson OSD. This is a synchronous OSD that is data load. Okay, it tries to bring high performance and low latency in the server side. Okay, so that's the introduction of myself and the team. Okay, so let's start the topic today. Okay, this is the agenda of today. So at first, I will explain why we do the work, and then give the detailed design and the implementation. And then I will show the performance reports. Okay, the first part, I will update our upstream status and future work. Okay, in the end, we will have open question part. But if you have any question during the session, please don't hesitate to ask. Yeah, I'm happy to discuss with you. Okay, so background and motivation at first. So, may I take a poll at first? So how many of you use Ceph for production here? Please show your hands. Okay. So how many of you are familiar with the Ceph? Oh, a lot of people. Okay. So I will have a quick introduction about Ceph. Okay. So Ceph is a unified distributed storage. It provides object, file, and block access. Okay, you can object is accessed through S3 interface or Swift interface, and the Ceph provides Ceph FIs for file access. For the block access, there are two ways. One is through the kernel driver, that is KRBD, and the other is LibRBD, which is in the user space. So our cache work stays in the LibRBD part, that is in the user space. Okay, so this is the overview of Ceph Cluster. There are at least 3 kind of loads in the Ceph cluster. Monitor loads track the active and failure loads and the configuration of the cluster. Such information manage load run alongside multi-load and provide monitoring and interfaces for external system. And OSD loads that are the data loads. The data are stored in these loads. By default, every data has 3 copies. These copies are replicated across OSD loads. So from the client side, the clients can access the OSD loads directly to get to site data. Okay, so this page, this page shows the the usage of Ceph Workloads. Okay, so Ceph has been used by infrastructure providers and enterprises for various workloads. The chart shows categorized of categorized of the workloads on a performance and capacity scale. The X refers to storage capacity and the Y refers to storage performance. Ceph has been popular for storage-oriented workloads. That is the workloads in the bottom of the chart. Okay, and for the workloads on the top of the chart, Ceph has been catching up. Some of the work Intel has been involved is improving this part. Okay. Okay, for the top of the chart, they ask for medium capacity but higher performance. Okay, in the bottom, they ask for a low they don't require high performance. Yeah. Okay, so this page, the left chart shows the average latency and tail latency. I did a simple test on a high performance SSD. I mean, I use the high performance SSD as a backend storage device and did the test, did 4K random write. Okay, you can see that the 4 lines latency is about 6 or 7 times of the average latency. That means the difference is big. And if you use low performance disk as a storage device, the difference will be increased. Okay, so we have monitored with some customers. They don't ask for very high LPS, but they have strict limitation about the tail latency. Okay, they would like to use database on Ceph. Okay, so we are going to improve the problem. From the server side, Intel is working with the Red Hat on Crimson OSD. This can improve the latency and bring high performance in the server side. And in the other side, we do some work in the client side. Yeah, that we would like to import persistent cache in the client side, which close to the application. Okay, so this chart shows the existed cache in the client side. Okay, here client side I just mentioned. I talked about the RBD inside. Okay, so currently RBD supports RAM-based block cache. Okay, so the cache is not persistent and it has small capacity because my memory is limited in current server. Okay, so to use high performance device like memory or SSD, we are going to introduce a persistent block cache in librd. Okay, here is the latest generation hardware for Ceph in Intel. Today I mainly focus on the Optane part. Okay, so Intel developed Optane 3D X-point technology to provide high performance, high endurance, and consistent latency compared to traditional SSD part. Okay, to get best use of this device, we would like to use it in the client side as the client cache. Okay, so the above part is the background and motivation part, and next we go to the design and the implementation. Okay, we are going to implement an ordered crash consistent write-back cache. Okay, to do this, there are mainly two kinds of methods. One is to use general write log. The other is to use snapshot. Okay, we use in the file system. Under the file system, we depend on write barrier to do this, because with write barrier, it will send sync or flash request to the block device, so that block device can persistent the cache data. Okay. So with the ordered crash consistent write-back cache, RBD images are consistent despite computer loads crash. Okay, so this page introduces the overview of the architecture of our write-back cache. Okay, we introduce three modules in the librd. One is the write log, which is responsible to flash data to the cache device. Okay, flash part is to flash cache the data to remote OSD loads, and the replicator is to replicate cache the data across several loads to make it a multi-copy. Okay, we have ever thought of we would like to launch a replica debug in the storage load. But currently this part is still in progress. Okay, so sorry, I forgot to mention, we will introduce the write-back cache on two kinds of media. One is in the PMIME and the other is on SSD. Okay, so let's introduce PMIME at first. So, as we know, persistent memory is byte addressable, non-volatile. We act it as memory. Okay, so to operate with the memory device, we use PMDK. PMDK is a growing collection of libraries which build on DEX features. It load or store. It direct load store access to persistent memory. Okay, so after that we can operate the memory device directly. There is a nib pmime object in PMDK. This library provides a transactional object store for catching metadata. Okay, so this is the data layout on persistent memory. There are three parts: the super block part, and the general array part, and the data buffer. The super block includes the overall information. The general array part includes a list of write log entries. Okay, every write request is mapped to a write log entry. Okay, so this part will be used repeatedly, like a ring buffer. Okay, and the data buffer is used to catch the data. So we use the library nib pmime object to provide transactional metadata store. For example, we updated the super block. We update the super block. We use nib pmime obj library to keep transaction, to guarantee the transaction. Okay, so this is the data layout. Catch the data layout on catch the SSD device, because SSD device can be only accessed based on a block size unit. By default, it is 4K. Okay, so on the SSD, it includes two parts. The first part is super block, and the second part is the ring buffer of spans. Okay, a span includes a control block and corresponding data. Okay, like pmime device, control block is a list of write log entries. The span are appended and accessed sequentially. And in the super block, the head will refer to the first valid span in the ring buffer, and the tail will refer to the first free space. Okay, so after we flash the data to the remote OSD side, we need to reclaim the cache space. So when we do reclaim, it is reclaimed on a span unit. Okay, here is the generic write workflow. Okay, the overall process is at first we receive requests from nib RBD, and then we save data in memory. And once we get a flash request, flash request, that is a sync request. Okay, and we will flash data to catch device. Later, we will destage data to storage cluster, that is OSD side, in backend, and then reclaim data space. Okay. In our write-back catch, we provide two modes, two persistent modes. Okay, so the first option is persistent on write modes. Okay, so the request is acknowledged only after it has been persisted to catch device. And on Persist-on-Flush mode, when the data is written to run buffer, we return to application that the write is completed. Later, after the user send out a flash request, the data and the former write logs and the corresponding data are flashed to cache device. Okay. Meanwhile, if the capacity of dirty data in the cache exceeds the limitation, or it stays too long time, we will trigger a sink. That means the former write log entry and data will be flashed to OSD device. Okay, so the policy is selectable. We can define it in the config file. Yeah, or it can be auto detected. Yeah. So that means at first it is under Persist-on-Write mode, and then when we get a flash request, we will change it into Persist-on-Flush mode. Okay, the following two pages. The following two pages are the detailed workflow and the two modes to give you a more clear introduction. Okay, so and the Persist-on-Write, when a write request is handled, it creates a write log entry and append it to a log queue. Okay, and then a sync point is inserted. Okay, so the log and the corresponding data are sent to the cache device, and then update the CO per block. After that, write completes. Right after that, it returns to the application that a write request is completed. This is the detailed workflow on Persist-on-Flush mode. Okay, so when a write request is arrive in our cache module, also it creates a write log, and the data is copied in the RAM. Okay, so after that, it returns to the application that the request is completed. Okay, so later, when users send out a flash request or some limitation are met, the former write log entries and corresponding data will be written to cache device and then updated CO per block. Updated CO per block to point to the next free space. Yeah. Okay, so this page is about flash mechanism and flash and reclaim mechanism. Sorry, I forgot to mention there are two differences between the two modes. One is when to return to the application, and the other is when to persist the write log and the data to the cache device. Okay, about the flash and reclaim, we flash write log entries on sync point boundary. That means between two sync points, the flash can be, we can flash the write request to OSD in parallel. Okay, once the write log is flashed to OSD, the log is marked as completed. Okay, meanwhile, we will do the write coalescing. That means we will merge several write requests which are on same object to just one write request and send it to the OSD. Okay. About after the cached data is flashed to OSD part, later we need to reclaim the cache space for later usage. Okay, so On SSD part, when log entries in a span are completed, the span can be reclaimed. Yeah, and also the spans are reclaimed sequentially. Okay, so that's all for the design and implementation part. And next, let us see the performance report. Okay. I did a test with FIO plus LibRBD. Okay, I did test on single RBD image and multiple RBD images. Okay, the left side shows the hardware and FIO configuration. Okay, I use Optane SSD as a cache device, and every RBD image uses 1 GB cache device. Okay, so I set the LPS limit as 4K and send the flash request or sync request every 32 32 IOs. And also I set the queue depth as 32. Okay, so I run 4K random write. Okay, the runtime is 10 minutes, and so that the 1 GB cache has been filled one time, and then start the second round. Okay, the runtime is 10 minutes, so that I can get a stable performance result. Okay, you can look to the right chart. Both the average latency and tail latency has been improved. Okay, the four lines latency is 94% better. Yeah, the unit is microsecond. Okay, and the second chart is to run FIO on multiple RBD images. And also we are in the same client load, and I create 5 10 GB RBD images, and every RBD images has 1 GB write space, cache space. And for every RBD image, I set the LPS limit as 4K. Okay, and then I can get the performance result on the right. Okay, also both the average latency and the TL latency has been improved a lot, and the 4 lines latency is about 98% better. Okay, the unit is microsecond. Okay, so let's go to the future work part. Okay, so about the current upstream status. Okay, about the persistent memory part. Currently, the PR has been submitted to the Ceph community, and it is reviewed by the LibRBD maintainer, and we are trying to merge it in Octopus release, which will be released next March. Okay, about the SSD part, currently it is under development. We are going to, our target is to merge it next year. Okay, to increase, okay, so currently our cache is just a single copy, and to increase the redundancy, we need to add replication support. And at first, we are going to add replication support on persistent memory over RDMA protocol. This lead PMDK support, and we are negotiation with PMDK team about our requirements. Okay, and the third part is about the CAS, that is Cache Acceleration Software. This has been a product in Intel. It provides cache functionality similar as Bcache. Okay, this year I remember it is open sourced, and you can find it in the GitHub. Okay, so currently there is a POC to integrate the cache in the RBD. Yeah, also you can find it in the GitHub. Yeah. About whether to integrate it, about how to integrate it in the RBD, this is still under discussion. Okay. Okay, so that's all for the content of today, and thank you. So any questions? Okay.
The replication of the cache is managed by Ceph to pick which node to be.
You mean replication? You mean replication the cache? No, we will have in the in the client side it is managed by the RBD, right? And but in the storage side, if we replicate the data in the storage load, we will launch a demo process to handle, not in the OSD. Yeah. Sorry. Yeah. In fact, this part is not very clear now. Yeah. So, any other questions? I think yeah. So no questions? Okay. So okay, thank you very much to join the session. And any other questions, you can talk with me offline. And if you need any cooperation about Ceph, also you can talk with me. We have a team. Okay, thank you.